Hey everyone, today we're going to look at questions 4 through 7 on the 2018 AP Chem free response section. So these are shorter. The ones on the test this year will be a little bit longer than this. They're not going to have any short ones. They'll have a regular long one, it looks like, and then one that's a little bit shorter than this. So let's take a look at what we have. In question 4, they want to know about the relative strength of the intermolecular forces and explain why the boiling point of CS2 is higher. So they're saying that this one has the higher boiling point. But if you look, it's a symmetrical molecule, so there's no dipole forces. It only has London dispersion forces. So that would be induced dipole. You could also say that. If you look at the second molecule, it has dipole-dipole forces because it's polar, because it's not symmetrical. But remember, the London dispersion forces are always there as you move up from lower to higher strength intermolecular forces. The lower ones still remain. So this actually has both. So you would expect it to be the higher boiling point, to take more strength to separate. But they're saying that that's not true. So really, you just take this information here about the boiling point and you say that the London dispersion forces of the CS2 must be stronger than the combined forces in the SCO of the dipole-dipole force and the London dispersion force. We know it has to be stronger because the boiling point says so. So just use their info, name each force present in each molecule, and then use your boiling point as your evidence. In part B, they want us to take the 10 grams of CS2 and we need to change it to moles so that we can figure out the pressure. So if we just divide by the molar mass of CS2, that will give us N. And in that case, it's 0.131 moles. Now, if we know the number of moles of the part we're talking about, we can determine the pressure of the part we're talking about. So we're just going to take our N and put it in here and use that to solve for the pressure. So the pressure is going to be nRT over the volume. And then you can just include all of the conditions that you have. We know that the number of moles is 0.131. We know our constant is 0.0821. We know the temperature is 325. And we know that the container is 5 liters. So you can use that to come up with your answer. It's supposed to be something like 0.7 atmospheres. That's how you can take care of part B. Let's look at the next part, which I think is this one. In question 5, they give you a weak acid, and they want you to talk about it being dissociated or not, and they tell you that only 13% of it gets dissociated. They want to know which picture represents that. Well, you kind of need to know what the little symbols in there look like. So if it's looking like that, that's an HF that's still together. It's not ionized, it's not dissociated. When it breaks apart, the hydrogen sticks to water, making H3O+. And then you've got the anion here. So these are the things you're looking for when it's dissociated. Well, figure 1 only has one like that, and in figure 2 they're all like that. So we want to say figure 1 because figure 2 is completely dissociated. So you can use that as your explanation. In part B, they want you to use the percent ionization to figure out the Ka. So I've got my icebox set up here. Remember, the water doesn't matter. And we know that before this dissociates, there's none of that going on. We know some of this is going to dissociate. In fact, they tell us that 13% of it's going to dissociate. So if you just take 0.013 times the starting amount, that tells us the amount that dissociates, and it's something like 0.00455. So that's going to get turned into our products. And once you know the amount of change, you know the amount at equilibrium as well. 0.00455. And then if you subtract these over here, that doesn't really change a whole lot. And then you can take these equilibrium amounts and put them into your equilibrium expression. So remember, that's products over reactants. So we're going to have 0.00455 squared for each of these over the part that didn't dissociate. And that is going to be our Ka. And so if you do that, you get something like 6.81 times 10 to the minus 4. So the only thing weird about that is you need to use the percentage of ionization to find out the amount that changes. Okay, in part C on this one, they're asking us, well, what if we throw in twice as much water? Because you're adding another 50 mils. So you're adding 50 to the 50 that's already there. So you're doubling the water, which means that you're cutting the concentration in half. So if you have 0.5 as much of this, and 0.5 as much of that, and 0.5 as much of this, when you go to cancel, one of these 0.5s cancels with one of those 0.5s, but the other one does not. So that the net result is that your Q is 0.5 times whatever it was. So it's not going to be the same. So your Q is going to be smaller than your Ka. You can do an equilibrium expression with that too if you want, or you can just explain it with the math. In number 6, we got a fun little electrochemical cell. Part A, they want to know, well, how come it's not showing any voltage? And it's because they forgot to put in their salt bridge. So that allows ions to travel from one side to the other, and that effectively carries the charge to complete the circuit so that electrons can flow all the way around. So talk about the ions in the salt bridge as a means for the charge and the completion of the circuit. In part B, for number 1, they want to know E for the cell. I think I have a picture for that. So remember that E for the cell is E for the cathode minus E for the anode. So we kind of need to know which way this thing's going. Let's see, they tell us that E for the cell is positive 1.54. So we know that it's spontaneous. We know that it generates electricity on its own. They tell us the half reaction for the silver is 0.8. So let's see. Galvanic cell. So it says the Ag plus ions are reduced. So here in the half reaction, it goes from +1 to 0. So if it's reduced, then this is the cathode, and this is the anode. So we know that we can put the 0.8 in for the cathode. And then you can do a little math and figure out the E for the reduction potential, for the chromium, and that's going to be a negative 0.74, and remember that's volts. They want us to write the balanced net ionic equation for the overall, and now that we know which one gets reduced, remember the cathode gets reduced, an ox, red cat, we need to reverse the anode. So we're going to switch the anode around, because right now it's written as a reduction. It needs to be written as an oxidation, because you got to have one oxidation and one reduction and a redox reaction. Now you can combine those together, but we have to multiply the top by 3 so that the electrons cancel out. So we're going to have 3 silvers, 3 electrons, and 3 silver ions. Now the electrons cancel, and we get something that looks like this, 3 Ag+. What else we got down there? We got a Cr. And then on the other side, you're just going to have the chromium ion and the silver. Don't forget the 3 that we added in there. So there's your overall equation. All right, then in part 3, they want delta G for the reaction. If you look on your equation sheet, there's at least 3 delta G reactions. The one you want for electrochem is always an Fe, where N is the number of moles of electrons. F is our buddy, the Faraday constant, 96,485 coulombs per mole of electrons. You don't have to remember that, just look it up on your chart. And then E is the E for the cell, which they told us was 1.54 volts. And so the N is the number of moles of electrons, and it's the number that you use right before you combine your 2 half reactions together. So in this case, that's going to be 3. So if you multiply all that together, we get negative 4.46 times 10 to the 5th. Negative meaning that it's spontaneous, energy is produced. 10 to the 5th because joules are kind of small. So a lot of times they might ask for that in kilojoules. Here they didn't, so it's just going to be joules. Okay, and then question 7 is a fun photoelectron spectroscopy question. So they give you the spectrograph here, and remember, wherever the big number is, that's closest to the nucleus, because that's going to take the most energy to remove. So wherever the big number is, the peak that's by that, that's your 1s peak. And then this just follows electron configuration. So if that's 1s, this is the same height, so that's going to be 2s2. And then we know what follows it is 2p, but because it's 30% taller, it's going to have more electrons in it. So instead of having 2 electrons, it will have 3. And if you look up something that has 2 plus 2 plus 3 electrons, 7 total electrons, I think you're going to find that that is nitrogen. In part B, they tell you that it's half-life. You want to remember that half-life is first order, or radioactive decay is first order. So you get to use this guy right here. Half-life is 0.693 over K. So if we know the half-life is 10 minutes, then we can just put that in and say 10 is 0.693 over K, and then we can solve for K. So that's going to be 0.069 minutes. Use the same unit of time that they give you. Oops, sorry, that's a per minute, because the minutes are going to be on the bottom. Now, in the last one, it says if there's 64 atoms, how long does it take for it to get down to 1 atom? Well, the key here is figuring out how many half-lives go by. So the way you can do that is just use this little equation, 2 to the n equals how many stuff you're trying to get. Or you could just do it on your fingers. You could just take 64 and cut it in half, 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 and then just count how many times you did it. So we know there's 6 half-lives. Well, if you do 2 to the 6th power, that's also 64. So we know that there's going to be 6 half-lives. Well, 6 half-lives is not the answer. They want to know how long is it going to take. Well, go back here and remember that the half-life is 10 minutes. So if I need 6 of those, then it's going to take 60 minutes. That'll be enough. So you get a point for that. Any way you explain it with the diagram, you could, or you could talk about this, just some way to show what's going on in your head when you do that. So there you go, some fun stuff. Tomorrow, sounds like we're going to talk about titration. So I'll find a good one of those for you, and I'll see you then.